Introduction of vector. Vector quantities are extremely useful in physics. The important characteristic of a vector quantity is that it has both a magnitude or size and a direction. Both of these properties must be given in order to specify a vector completely. An example of a vector quantity is displacement. This tells us how far away we are from a fixed point, and it also tells us our direction relative to that point. Vector is represented geometrically as direct line segments or arrows in 2-space or 3-space. Next, we have an example formula of vectors. First, we have triangular law of addition, and second, we have parallelogram law of addition.
Next, history of vectors. The concept of vectors was not created by a single individual but rather evolved over centuries through the work of numerous mathematicians and scientists. However, key figures contribute significantly to its development. It was invented by Josiah Willard Gibbs and Oliver Heaviside at the end of the 19th century. Josiah Willard Gibbs. Gibbs, an American mathematician and physicist in the late 19th and early 20th centuries, made substantial contribution to vector analysis and its application to physics. He plays a crucial role in formalizing vector calculus. This solitarily developed vector analysis to press out the new laws of electromagnetism discovered by Scottish physicist James Clerk Maxwell. This allowed scientists and mathematicians to calculate such things as speed and direction from a graph. The second one is Oliver Heaviside. Heaviside and Gibbs independently developed a roughly equal way to digest working with vectors, giving us the now familiar resultant, dot product, cross product, and so on. William Clifford developed a contrasting known as today as Clifford algebras, which have the supremacy of being more universal to higher dimension. Cross products are only defined for 3 dimensions, but are not as well known or used as the vector of Heaviside and Gibbs.
So we move to the vector application in aviation industry. So the application vector are integral to many aspects of the aviation industry, from flight planning and navigation to performance calculations and safety measures. Application flight planning and navigation. Route planning. Vectors are used to determine a most efficient flight paths. These paths are represented as vectors connecting waypoints, ensuring the aircraft follows the correct route. Second, great circle navigation. Since the Earth is a sphere, the shortest path between 2 points is an arc known as a great circle route at a subheading. So second is position and movement. Position. GPS and other navigation system use vectors to determine the aircraft position relative to the Earth's surface. Second, velocity and acceleration. The aircraft velocity, speed and direction, and acceleration, change in speed and direction are represented as vectors. Third, orientation and heading. First, heading. The direction the aircraft is pointed, represented as a vector, is crucial for navigation. Pilots use heading vectors to maintain course and reach their destination. Second, bearing. Vector represented the direction from the aircraft to a particular point, such as a waypoint or a runway. Bearing are essential for navigation and landing procedures. Fourth, autopilot and flight management system. First is navigation. Autopilot system use vectors to maintain the aircraft course, altitude, and speed. This system continuously adjust the aircraft control surface to follow the desired vectors. Second, flight management. Flight management system, or the other name is FMS, use vectors to optimize flight paths, fuel consumption, and overall flight efficiency.
And now I will explain about the example of vector. Vector are a cornerstone of the engineering mathematics, representing quantities endowed with both magnitude and direction. Here are three examples for vector commonly encountered in the field. Firstly, electric field vector. Electrical engineers often work with electric field, which are vector quantities. The electric field vector represents the force per unit charge exerted on a small positive test charge placed at a point in space. For instance, if an electric field is directed straight downward with a magnitude of 500 newtons per coulomb, it can be represented as like the picture. Secondly, force vector. In mechanical engineering, force are often represented as vector. For instance, if a motor applies a force to a gear, this force can be depicted as a vector. Suppose the force has a magnitude of 200 newtons, direct 30 degrees above the horizontal plane and towards the east. The force vector can be expressed in its component form, considering the magnitude and the direction it's applied in. Lastly, velocity vector. Aerospace engineers frequently work with velocity vectors to describe the motion of aircraft. A velocity vector indicates both the speed and the direction of the aircraft's movement. For example, if an airplane is flying at the speed of 250 meters per second, heading 50 degrees north of east, and climbing at an angle of 5 degrees, its velocity vector would provide a comprehensive description of the trajectory through the air.